MCQs related to acid-base equilibria. We did some of the questions. We'll now do specifically question related to the buffer. Question 7. The question is a buffer solution of a 0.1 mole per dm cube with respect to ethanoic acid and 0.05 mole per dm cube with respect to sodium ethanoate. And the dissociation constant is also given, which is 1.7 exponent 5. What the pH of the buffer solution? So they already provide a buffer solution has a concentration, like we have a mixture. Already there is a mixture. What is a buffer solution? A buffer solution is a mixture of a weak acid and its salt or weak alkali and its salt. So this is the acidic buffer solution because ethanoic acid is there. So we have an acid, the ethanoic acid, and what is the concentration of ethanoic acid? 0.1 mole per decimeter cube. And we have the salt is also there, sodium ethanoate, which is a salt, and the concentration of a salt is 0.05 moles per dm cube. We need the pH of this buffer solution. To get the pH of the buffer solution, we need the hydrogen ion concentration. What is the formula to calculate the hydrogen ion concentration? The hydrogen ion concentration is equal to dissociation constant Ka times the concentration of acid divided by the concentration of a salt. And we already have the concentration of acid and a salt. So we just need to get the hydrogen ion concentration. So what is the hydrogen ion concentration? So H plus ion concentration, this is 1.7 exponent minus 5. The dissociation constant is there. The concentration of acid is 0.1 and the concentration of a salt is 0.05. When we simplify, this will give us the hydrogen ion concentration. What's a hydrogen ion concentration? 1.7 exponent negative 5 times 0.1 divided by 0.05. That's 3.4 exponent negative 5. Okay. So that is equals to 3.4 into 10 to the power minus 5. That's a hydrogen ion concentration, but we need the pH of the solution. So to get the pH, the formula pH is equals to minus log of hydrogen ion concentration. So minus log of H plus ion concentration, which is 3.4 into 10 to the power minus 5. So what is the log of 3.4 exponent minus 5? That is 4.47. So pH is equals to 4.47. So 4.47, we got B as the right answer. So this is a straightforward question related to a buffer solution. They already give you the concentration and you just have to work out the pH. Is it clear, this example? The next question, this equation for a reaction between a weak acid and a sodium hydroxide. The pH of a solution of a salt is most likely to be, look, when we talk about the weak acid and the salts, if we have a weak acid, it will have a strong conjugate base. If we have a strong acid, it will have a... So the equation for a reaction between a weak acid and a sodium hydroxide is there. the pH of a solution for a salt NX is most likely to be. Like this salt is there. What could be the pH of this salt? So how this salt is produced? When HX, like the any acid is there, it reacted with sodium hydroxide. This will result in a formation of like a salt plus water. The question is, what is the pH of this thing? Like a NaX. So how we can identify, as we know, it's a weak acid and it's mixed with a sodium hydroxide. Sodium hydroxide is a strong base. And weak acid, their base will be conjugate. So they're not asking about sodium hydroxide, they're asking about this salt. So what will happen? The solution will be alkaline because a strong alkali is added. So the solution will be alkaline. If a solution is alkaline, it cannot be A or B. Why it cannot be A or B? Because it's a strong alkali is added. So solution must be alkaline solution. Then what about the options are there above 7? So we have 8.5 and 13. 13 is the pH for a strong base. They're not asking for sodium hydroxide. If they ask us for sodium hydroxide, we'll select D. But what they're asking for a salt which is produced by the weak acid. So weak acid will have a conjugate base. So actually what they're asking about the conjugate base. So the conjugate, because it's a conjugate base, that's why it is 8.5. Is it clear? Another question, as you can see, related to the buffer solution. When a small amount of a hydrochloric acid is added, the change in pH is very small. What is the best explanation for this? Like when we are adding a small quantity of a hydrochloric acid or HCl, there is a change in pH, but the change in pH is negligible. Look, remember one thing, that for a buffer solution, the hydrogen ion concentration is equals to Ka, the concentration of an acid, divided by concentration of the salt. Okay. So what happened when we are adding an acid means the amount of acid is increasing, but already the amount of the salt of the negative ion is already more. So if I say 2 divided by 1000, or if I say 3 divided by 1000, if I say 4 divided by 1000, the fractions won't change much, even though the numerator is increasing, but the increase in numerator is negligible as compared to the denominator. In a buffer solution, we have a reservoir of a salt. Reservoir of a salt means like we have too much negative ions. So this factor, even though we are adding an acid, the amount of hydrogen ion increases, but this fraction won't change much. That's why the pH does not change. So when a small amount of a hydrochloric acid is added to a buffer solution, the change in the pH is very small. So what is the reason for that? The reason is that the ratio of the concentration of acid and the conjugate base, because salt is also called a conjugate base, in the buffer solution does not change. Because as this ratio does not change, that's why the hydrogen ion concentration does not change, or the pH of a buffer solution remain constant. So whenever we have a buffer solution, this ratio remain constant because we have a very large number of a denominator. Look, when we talk about the buffer solution, a buffer solution is formed by a mixture of weak acid and its salt, or weak alkali and its salt. Example, we have a weak acid which is CH3COOH. It will dissociate into what? It will dissociate into CH3COO negative and H positive. And a salt is there. So let's say CH3COO-Na. So this will produce CH3COO negative and Na positive. Okay. Now, when we write the equation for a hydrogen ion for this buffer solution, the hydrogen ion is equal to Ka, the dissociation constant, concentration of acid. The concentration of acid means like CH3COOH divided by the concentration of the salt or the negative ion of the salt, which is CH3COO. Now what happened? As you can see, that this negative ion, CH3CO and CH3CO, it's coming from both molecules. It's coming from the acid and it is coming from the salt. So we have a reservoir, or we have too much of the conjugate base. You can also say as a conjugate base, or you can also say a salt. So we have plenty of a salt. Okay. Now, if we add an acid, so if we have a plenty of a salt, it means the denominator is a very large number. So this denominator is very large. Like example, if the molecule of the acid, let's say it was 10, but the molecule of the salt are too many, like example, maybe 10,000 or 100,000. Now what happened? If I add an acid, if I add H plus ion, when a small amount of H plus ion is added, so this H plus ion can react with either any of this molecule and it will form an acid molecule. Like it can react with any of the negative ion to form an acid molecule. So when it form an acid molecule, the amount of acid molecule increase. But how much it will increase, like how much we added. Like if I add 1, it will increase by 1. So what the fraction will become? It will become 100 divided by 100,000. So 10 divided by 100,000 and 100 divided by 100,000, it's a negligible change, like it's not a considerable change in this fraction. So this ratio of the acid and the salt remain unchanged even though we are adding an acid. That's why the hydrogen ion concentration won't change, or the pH of the solution does not change. Is it clear? So that is what they said. The ratio of the concentration of acid and the conjugate base in the buffer does not change. So the pH won't change. The conjugate base, the salt is also called a conjugate base. This is the conjugate base. This molecule. Why we called it a conjugate base? Because for acid, there's a conjugate base. If you remember when we wrote the reversible equation, so when this acid will dissociate, it will dissociate into CH3, CO negative and H positive. So this is an acid, but the reverse reaction, this is a base. So we don't call it a simple base, we call conjugate base because it is accepting proton. So this molecule is called a conjugate base, which I was writing as a salt as well, because so usually they give you the salt rather than saying a conjugate base. So more we'll do in the next session.